Okay, let us start our second of this session. Our speaker is Tianqing Zhu from Tsinghua University.
Yes, so I'd like to first thank the organizers of the workshop. It's a really wonderful workshop. And today, actually, my topic is about from the quantum difference equation. So actually, it's a little bit puzzled that maybe you're a little bit puzzled at what is the quantum difference equation, what is the Maulik-Okounkov quantum algebra. But I will introduce both of them later. Yeah. So let me first start with how to look at the quantum domain algebras from algebra geometry. This is a very, very rough introduction of this. So it is well known that for the quantum algebras, all the quantum groups actually has two types of the realization. So the first type is a dream field realization, and the second type is the RTT realization. So in the brief description, that in dream field realization, the quantum group is generated by the generators generating functions of the generators. For example, you have the positive root vectors and the negative root vectors. But in RTT realization, the quantum group is generated as the matrix coefficients of the R matrix. For example, in the typical example of the Yang GLN, this algebra, you can think about this algebra as being generated by the matrix coefficients of the standard R matrix. And each realization can show that both of the realization give the same associative algebra, but each realization actually shows the different aspects of the quantum affine algebra as the Hopf algebra. So what does mean? It means that they have the same associative algebra structure, but they have the different Hopf algebra structure. But from the side of the geometric representation theory, the dream field realization usually corresponds to the K-theoretic whole algebra realization. Roughly speaking, you can think about it as the equivalent K-theory of the modulus stack of quiver representations. Well, the RTT form realization usually corresponds to the stable envelopes realization. And this is, you can think about this as some K-theory class, which is explicitly the Steinberg correspondence class in the K-theory of quiver varieties. So this is a little bit abstract for the second one. Yeah. So actually, it has long been conjectured that for arbitrary quiver Q, such two realizations will give the same Hopf algebra. Give the same associative algebra. This is a typo, sorry. In this talk, actually, I will show that this is true in the case of the affine type A. And the techniques I'm going to use is related to the quantum difference equation in the title. Yeah. So the main geometric object today is the affine type A quiver varieties, as I have mentioned for the RTT realization in the introduction. So what is the affine type A quiver varieties? So let me give a brief introduction. So the affine type A quiver variety will first start with the quiver representation space. So you can see that it is a bunch of the linear morphism between different vector spaces. And for the first part, like the vector spaces denoted by V, we usually call this as the quiver representation of the gauge knots. But for the vector spaces that has been denoted as Wi, this is usually called the frame knots. And both of these terminologies are from the physics. And And actually, you can see that for this type of the quiver representation space, this is a linear space. And to be honest, this is actually a symplectic vector space with a natural symplectic form, because you can think about the second term in the direct sum to be the dual of the first term. So you can see this is a symplectic space, and this space actually has a really natural group action given by the automorphism of the gauge knots, which is the automorphism of Vi and the automorphism of the Wi. And at first, we're going to use the automorphism of the Vi, which will give you a Hamiltonian action over this representation space. And since this is a Hamiltonian action, actually you can see that this will give you a moment map. And I haven't written up a moment map here, but yeah, actually, but the thing is that after having this moment map and you fix a stability condition for this quiver variety, you can do a GRT quotient. You can do a GRT quotient over the inverse image of the moment map, and this will give you the affine type A quiver varieties here. So this is the definition for it. Oh, sorry, this is for these two whites. And moreover, I didn't explain here. Yeah, I didn't explain here. So actually, this quiver varieties are actually good it is good in the sense that it is a smooth quasi-projective variety, which is also symplectic. And the symplectic structure also comes from the symplectic structure of the symplectic vector space. Yeah. And over this quiver variety actually has two types of the torus section. So the first type of torus section is really natural. It comes from the maximal torus of the automorphism group of the frame knots. And the second one is the two-dimensional torus section acting on these quiver varieties. And the action is given in the following way. So it has two, so we denote the corresponding co-character as Q and T. So we denote the product of two torus as T. So actually in today's talk, we'll mostly use the equivalent K-theory of quiver varieties. So it will be written in this form. And we always fix the stability condition to be 1, 1, 1, 1, 1. And for the generators of this equivariant K-theory, you can see that by the Cohen surjectivity, it is usually generated by the co-characters of the torus and the topological bundles over these quiver varieties. Yeah. So here are some examples for the affine type quiver varieties if you're not familiar with this terminology. So if I take n equals 1, this quiver variety will become the modular space of torsion-free sheaves over P2, which is trivialized over a line at infinity. So if you take arbitrary n and we take the frame vector to be just the unit vector as some direction, and we take the gauge vector to be all equal like L, 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 L. In this case, this quiver variety will be isomorphic to the Zn equivariant Quiver scheme of points over C2. Yeah, and moreover, if we take the stability condition to be of the opposite one, this quiver variety can be described as the modular space of the equivariant torsion-free sheaves over the n-1 surfaces. So you can see that there are a lot of good geometry inside of this quiver variety models. And so you can see that this is really good from geometry side. So how does it go with the construction of the quantum affine algebra? So the quantum affine algebra constructed using the geometric side of the RTT formalism is called the Maulik-Okounkov quantum affine algebra because it was first proposed by David Malik and Maulik-Okounkov in the paper when they try to construct the Yangian in the geometric sense. So before we start with before the MO quantum affine algebra, we're going to start with some basic notions about the fixed point of the quiver varieties. So we're going to use some simpler notation, like we use this MW as the disjoint union of the quiver varieties summing over all of the gauge vectors, and we choose the subtorus inside of GW such that this subtorus will give a decomposition of the dimension vector W as A1 W1 plus until the AK WK. And the corresponding A fixed point is actually, you can see that it is isomorphic to the product of the quiver varieties of the smaller dimension vectors. So using this inclusion map, we introduce an injective map of the as the KT point algebra. And moreover, this is an isomorphism after the equivariant localization. And this is a standard result as the result in the equivariant cohomology case. So, and now we fix a Schember inside of the real Lie algebra of the torus A. Usually, maybe I should say it's a dual Lie algebra. So, and we also choose the polarization for the tangent model of the quiver varieties, and we also fix a fractional line bundle for the picker group of the quiver variety. Sorry, this X is just the quiver variety. And the K-theoretic stable envelope is an integral K-theory class. Actually, it is a unique integral K-theory class inside of the product of the fixed point and the empty space of the K-theory, which can be thought of as an isomorphism from the K-theory of the fixed point component to the empty space. And it satisfies the following condition. So the first condition is that the support of this K-theory class is in the 4 attracting set for the fixed point component. So how to explain this 4 attracting set? So you can think about this 4 attracting set as the closure of the attracting site with respect to the fixed point component. And what does it mean? So So intuitively, you can think about this condition to tell you that this stable envelope is block up triangular with respect to the partial ordering over the fixed point component. And there are some other degree bounding condition for this kind of condition here. But the most obvious observation that it is block upper triangular matrix. And the second one is that if you restrict the stable envelope to the diagonal, it's just the multiplication of some topological bundles of it. So you can see that So the first term over here, it depends on the polarization of the tangent bundle, and the second term it also depends on the polarization. It is the negative part of the normal bundle with respect to the fixed point component. And the third condition is I think is one of the most important conditions over here. So if you restrict the components to the off-diagonal ones or the stricter upper triangular ones, you can see that there's a degree bounding for this stable envelope. And this degree bounding, it means for the A degree, because when you restrict to the fixed point component, it's really natural to have this kind of decomposition as the Laurent polynomial over the co-character of A. Here, this degree is, so if you have the Laurent polynomial over some variables, you can associate a Newton polytope corresponding to the coefficients whether it should be 0 or not, as the corresponding space of degree for this Laurent polynomials. And so roughly speaking, the stable envelope is an isomorphism of the localization, and it is a block upper triangular matrix with respect to the partial ordering of the fixed point component. And if you do some actually from this condition, usually one can prove that this stable envelope is actually locally constant over the change of the slope points. So it will only change when the slope points went through some hyperplane. It means that if you have 2 points over the pickup space, and if you want the stable envelope to change, the necessary condition would be that these 2 points must be separated by a wall. So the corresponding hyperplane will be called wall for the stable envelopes. And I have to apologize because I don't have too much good example for the detail of this definition. But yeah, I just tell you some. So I will omit most of the details and tell you the rough story about it. Sorry for this. Yeah. And so we have defined what is the geometric R matrix. We have defined what is the stable envelope. And there's one thing I have to comment, that the existence of the stable envelope usually is really hard to prove. Well, the most recent proof actually depends on, there are 2 types of proof. The first proof for the quiver varieties, it depends on the existence of the stable envelope for the elliptical homology. And the second proof is done by doing the induction over the stratification of the attracting subset. So both of the proofs are actually very like some abstract. And so after the stable envelope, we can define the geometric R matrix as the composition of the stable envelope of one fixed chamber, together with the inverse of the stable envelope of the inverse of the opposite of the chamber. So you can see that because the inverse of the stable envelope is actually well defined after localization. So you can think about it as the endomorphism of the corresponding vector space over here after doing the localization. And also this space, actually they are all being localized. And furthermore, one of the good properties for this geometric R matrix is that the geometric R matrix can be factorized into the Ferlin process. So you can see that this is why this is called the geometric R matrix, because if you think about this KW1 to KWK as the space of states for the particles, this is like a 2-to factorization of the scattering matrix over here. So each part of the geometric R matrix, like this RCIJ, it is also a geometric R matrix constructed by the stable envelope. And moreover, you can check that it also satisfies the trigonometric and Maxwell equation. And using this kind of principle, you can see using the RTT formalism, one can use this definition to define the Maulik-Okounkov quantum polynomial.
Can you just clarify? So you mean the spectral parameter within Jambakh's equation?
Yeah.
Multiplicatively?
Yeah.
Are you saying that all these factors are trigonometric? matrices.
Right.
Depends rationally on this.
Yeah, exactly. Yeah. And one of the good properties for the ML quantum algebra is that it turns out that you can do such a factorization, wall factorization for the geometric R matrix. And usually this is of the Tolstoy type factorization. So what's the meaning of this factorization? It's like for each of the wall R matrix over here, like RW plus and minus, it is still defined as the composition of the stable envelope, but it's the composition of the stable envelope with the same chamber, but with a different slope points. And the W stands for the wall, and S1, S2, these two slope points stand for the 2 points on both sides of the wall. So, and you can also check that each of the walls R matrix also satisfy the Yang-Baxter equation. So you can still use the R2T formalism to define the wall subalgebra. And if it's actually denoted in this way, yeah. Oh, sorry. Actually, maybe later I try to denote it by the UQM because I'm going to define some other algebras later. Yeah. So in general, what does it mean for this factorization? So it means that the ML quantum algebra is actually generated by the wall subalgebra and the tautological classes for the equivalent K-theory of the quiver varieties. And the first is really obvious, and the second one is just because that if you compute the core parts, this R infinity, actually this is a block diagonal operator, and this operator is generated by the tautological classes. Yeah. So for now, for now, this is the motivation of the most primary motivation for the work. So the primary motivation comes from the K-theoretic quasimap counting to quantum groups. So the motivation of the work comes from understanding the K-theoretic quasimap counting of affine type A quiver varieties on the side of the representation theory of the quantum affine algebras. So the quasimap counting is similar to the Gromov-Witten counting, such that it counts the map from a curve to a geometric quotient of something of the stable points in the space W, but we allow that there are some isolated points in C being mapped to the unstable points. So this is like a rough definition for the quasimaps. And the target here today, for this geometric quotient is the affine type A quiver varieties, as mentioned before. And the corresponding quasimap modular space is the modular space of the quasimap from genus 0 curve C to the quiver varieties, which has the relative condition over P1 and non-singular condition over P2. And it's not, so if I want to explain what is the relative condition and the non-singular condition, you can think about the non-singular condition as the point P2 will be mapped to the stable points instead of this geometric quotient. The relative condition means that it will be mapped to the stable points after doing some resolution of this curve. So this is like a rough definition for the rough description of the quasimap with these two conditions. And also, it is known that this modular space is very good. What does it mean? It means that it has a perfect obstruction theory, which means that we can construct the twisted virtual fundamental shape of the modular space. And also because we know that we have some conditions over the point P1 and P2, so we can have a natural evaluation map from this modular space to the product of the quiver varieties. And using this kind of thing, you can define the capping operators as the push forward of the virtual fundamental sheaf with respect to this evaluation map. Because we know that this modular space is actually parameterized by the degree of the quasimap counting. And the degree of the quasimap counting is defined as the line bundle. It's determined by the line bundle over the quiver varieties, which is as the pickup group of the quiver varieties. So, but also this map is only proper after doing the localization with respect to the C direction. And this C direction comes from the automorphism group of the genus 0 curve. So you can see this class is it lies in the localized K-theory of the product of the quiver varieties. Here, this U is the equivariant parameter from the torus, and this Z is called the Taylor parameters. And we can think about this J as the isomorphism of one piece of this quiver, of this equivariant K-theory of the quiver varieties with the Taylor parameters Z. Yeah. And so it has been approved by Okounkov and Smirnov that this capping operator actually satisfies the following difference equation on Taylor variables and equivariant variables. So the first one is is the difference equation over the scalar variables, and the second one is the difference equation over the equivariant variables. So the main topic today is on the first difference equations. The operator here is usually called the quantum difference operator. It turns out that the difference equation can be transformed to the difference equation that has the origin in the representation theory of the Maulik-Okounkov quantum algebra. So, for example, for the quantum difference operators over here, it turns out that you can just write this quantum difference operator in terms of the product of some constant operators with a line bundle and the order product of the following monodromy operators over here. And this is called the monodromy operator. And here, the monodromy operator is defined the following way. So we fix a Worcester algebra over here, and for each Worcester algebra, we can have the following equation, which is called the ABRI equation. So the meaning of the equation is that the solution is called the fusion operator, and the fusion operator satisfies the equation such that this Z1 minus 1 is the multiplication of some scalar variables, and this Q omega, you can think about it as the elements of cotton inside of this Worcester algebra. And actually, you can see that this equation actually has a really unique solution. So in this way, it turns out that we can use this fusion operator to define the monodromy operators over here. So it's like we do the transpose of this fusion operator and do some multiplication, do some scaling over the scalar variables, and then compose it with the antipode map, and then we do the multiplication map from the left hand side and right hand side of the tensor product. So it turns out that it's been proved by Okounkov and Smirnov that this quantum difference operator is actually independent of the choice of the path from 0 to the minus L. And moreover, that this is TL prime minus 1. Yeah. So moreover, this difference operator, they will become a holonomic difference module over the Picard torus. So actually, you can think about it as some quantum integral system over the Picard torus. So this is the geometric story of the quantum difference operators. So the next thing we're gonna do is to do that. We can see that for now this difference equation is constructed on the geometric quantum groups. So for now we're gonna construct the quantum difference equation of the algebraic quantum group. What is the expectation of the Maulik-Okounkov quantum algebra in the finite way? So the expectation is the quantum toroidal algebra over here. So the quantum toroidal algebra, the definition is a little bit complicated. So I just introduced the non-negative part of the definition. So you can think about the quantum toroidal algebra as an algebra over the rational field of the field of the rational functions generated by the following currents. And the currents just means that the generators of the algebra is encoded by the Lagrange extension of this EIZ and FIZ and FIZ. But now I will only write down the relation for ER and phi plus Z. So the relation is written in the value. And here, this with the set relation, I did write down the set relation. And this zeta ijx is a rational function defined in value way. Yeah, so this bracket stands for the quantum number. Yeah. And moreover, one can define, for the convenience of the use of in the following talk, one can define the non-positive and the non-negative part of the quantum toroidal algebra. So for the non-negative part, it is defined as the algebra generated by EI and phi plus. And the non-negative and non-positive part is generated by the FR and phi minus. And the rest of the relation that I haven't written down can be deduced by the non-degenerate Dirichlet pairing for this non-negative part and non-positive part. And the Dirichlet pairing is uniquely determined by the Dirichlet pairing between the cutting currents and the generators of the positive part and the negative part. And with respect to this Dirichlet pairing, you can see that we can have a unique universal R matrix. Wherever this universal R matrix could lead us to the coproduct, which can be defined in following one. I still just write down the non-negative part. For the non-positive part, you just on your side. Okay. So the thing that we want for the toroidal algebra is that we know that for the M quantum fine algebra, it has a good wall factorization, which means that it can be generated by the walls of algebra. So the thing is that how we can realize the walls of algebra inside of the quantum toroidal algebra. It turns out that actually it can be realized, but we need to have some good algebraic model for this realization. So this realization is usually called the shuffle realization of the quantum toroidal algebra. So, but we have seen that this quantum toroidal algebra it can be uniquely determined by the non-negative half. And from the Maulik-Okounkov quantum fine algebra, we know that the quantum currency is usually generated by the tautological classes. So what does it mean? It means that actually we just need to determine the algebraic model for the EI current, which is the positive path, and then we can determine everything for this. And then we can determine everything for this quantum toroidal algebra. So we can see that this shuffle algebra realization, it usually specifically speaking, it means for the realization of the positive part of the quantum toroidal algebra. So how to construct this shuffle realization? So at first, we need to consider a really, really big vector space of the color symmetric. Sorry, this is the color symmetric rational functions, not the polynomial. Sorry. Yes. And here's so what does it mean for the color symmetric? The color symmetric means that for the first symbol over here, this is the color, and the second symbol means the variable. So the color symmetric means that if we fix the color of the variables, it will be symmetric with the same color. And we define a shuffle product of this big vector space, which is defined as, so suppose that we have a element in the, I have a function of n variables and a function of n variables. The result of this composition of this shuffle product will be the function of n plus n variables. So what this means? It means that we have the product of the f and g, which will be symmetrized. And before doing the symmetrization, we also twist this product with the product of the rational functions over here. And to be honest, actually, at first it's really puzzling. It's really puzzling because we don't know, because if you don't know the geometric origin of this product, usually we don't know why we should twist this kind of function. But actually, this is really natural if we do the. Oh, sorry, I haven't. Yeah, it's really natural in the geometry because this shuffle algebra is just the algebraic model for the localized version of the pre-projected K-theoretic algebra of a point of A. So I didn't say anything about what is the K-theory, what is the K-how, or what is the K-theoretic algebra. But you can take it for granted that, okay, we have an algebraic model for this kind of story. So the thing is that the big vector space is not the space that we finally needed. The space that we really need is a small subspace, which I shall call it the small shuffle algebra. So the small shuffle algebra is the sub-algebra of V generated by the monomers of arbitrary degree. And it turns out that it's been proved by linear goods that there is an algebra isomorphism between the positive part of the quantum toroidal algebra and the small shuffle algebra. And the map is just you send each of the generators to the monomers. And this proves it. Actually, I cheated a little bit because actually to prove this theorem, we need to use some results, and I'm going to show it later. But for now, you can just take it for granted. Okay, we have this kind of result over here. So I mean that if you want to prove this result, actually we really need the definition of what is the walls of algebra instead of this shuffle algebra. But for now, you can just take it for granted. And moreover, there's one comment for this small shuffle algebra is that we can see that for this shuffle algebra, you have two types of the gradation. The first gradation is by the number of the variables, so as we have shown before, and the second gradation is by the degree of the Laurent polynomial over here, or the degree of the rational function over here, because it makes sense to speak about this degree because this is a natural generated by the monomers. So we can have a natural decomposition of this vector of this small shuffle algebra as a vector space. Yeah. And for now, we're going to show what is the algebraic analog of the walls of algebra over here. So the algebraic analog of the walls of algebra over here is that we can choose what is called the slopes of algebra inside of this shuffle algebra. So for the positive half of the shuffle algebra, and we fix a slope point, which is the rational vector, we define a subspace of the slope smaller or equal to m as the Filling type. So let me explain the definition over here. So the definition is the following: like we choose a function inside of this space, and we do the scaling over some of the variables inside of this space, such that we send the scaling to the infinity, and the slope being smaller or equal to m means that this function will have the symptotic behavior as this power of the chi over here, with arbitrary a and b in the number of the variables over here. And this m is just the m. Sorry, this m is just the m that have been defined over here, and this inner product a and b is defined using the Carter matrix of the affine type equivalent varieties. So inside of this slope space, we can define the positive part of the slope subalgebra as the intersection of the greedy pieces of the shuffle algebra with this space, such that we need to require that the degree of the elements inside of this space should be equal to the inner product of the slope points with the number of the variables. And now using the similar delink theorem, one can define the whole shuffle algebra as the Drinfeld double of the shuffle algebra over here. And the corresponding slope subalgebra can be also defined using the similar picture. So I will denote it by S and Bm. And so maybe I can explain a little bit about the motivation for the definition of the slope subalgebra. The main motivation is that because we can see that for the definition of the wall subalgebra, it is dependent on the choice of the wall. And the wall is a codimensional one subspace in the. Sorry.
Remember, this high order representation is related to one of the.
Yeah, exactly. It depends on the slope. Yeah. So actually, in the case of n+1, because in this case, the bigger space is one. Yeah. That's just one dimensional. So the wall and the point and slope are the same.
Okay, and for n, for S1?
Well, S1 actually is like, so for the wall subalgebra is determined by the hyperplane, but here is the point. So the meaning of this is that it is generated by the wall subalgebra that has the point over here. So this is the motivation for this definition over here. And you can see that this is not that refined. This is not as refined as the definition of the wall subalgebra, but later we'll see that it can be refined. Yeah. So the first good thing about slope subalgebra is that this will give us a factorization of the quantum toroidal algebra. So what does it mean? It means that for this algebra over here, for the quantum toroidal algebra over here, we can factorize this algebra as the infinite product of the slope subalgebra over here. And moreover, this factorization preserves the whole theory for both the slope subalgebra and the shuffle algebra. And moreover, we can have for the case of the affine type A, we can have a much better description for the slope subalgebra. It's isomorphic to the product of the quantum affine GLK over here. So the description of the rule for determining the number of LH over here is a little bit complicated. But for the case of, for example, if you take the slope points to be an integer point, this slope subalgebra will be isomorphic to just the UQG hat over here.
What's LB?
Sorry?
What's L sub B?
LH is some integer number that is dependent on n.
Okay.
Yeah, I think I said here because it's a little bit complicated to determine this. Yeah. And so these are some introduction for the quantum toroidal algebra and its slope factorization. So what's the relation of this quantum toroidal algebra to the Maulik-Okounkov quantum affine algebra? And it has been long conjectured that the quantum toroidal algebra is isomorphic to the M quantum affine algebra. And the first computation is given by Negus that if you compute the full attracting subset near the diagonal, you can prove that actually there's an algebra embedding from the quantum toroidal algebra to the Maulik-Okounkov quantum affine algebra. And moreover, this algebra embedding, it integrates the action over the equivariant K-theory of the quiver varieties. And here the action from the quantum toroidal algebra is given by the action constructed by Hierogonic Gima. And the second action of the M quantum algebra is the natural action by the stable elements. But you can see that the injectivity of this map has been proved. But for the surjectivity of this map, it's very hard to prove because it requires you to fix the number of the generators on both sides. So actually, this is the topic of the talk today. So we're going to show that actually the corresponding isomorphism can be much more refined using the computation for the quantum difference equations. So for now, we're gonna go to what is the quantum difference equation from the quantum toroidal algebra side, and I should call it the algebraic quantum difference equation. So the algebraic quantum difference equation is defined as in a similar method for the geometric quantum difference equation, which is the Okounkov Smirnov quantum difference equation. So as before, so maybe we can. Sorry. So maybe we can recall something for the geometric quantum difference equation, that we know that for the geometric quantum difference equation, it is the basic data is that we fix the Walser algebra and we choose the APR equation over this Walser algebra, and then define the monodromy operators, and then do the ordered product of this monodromy operators with the line bound over here. So the basic logic is really similar. The basic logic is that we consider the slopes of algebra, and we consider the APR equation for the slopes of algebra. So the corresponding solution will be the fusion operators. And actually, I have omitted lots of the details over the side. But actually, you really need to do something to take efforts to prove that this APR equation is actually well defined. And for now, actually, you can see that if we have the solution of this APR equation, we can define the algebraic monodromy operator over this equation as just as the one before. And this is, I haven't changed the notation here, but this is the slopes of algebra. Sorry. And using this information, we can define the algebraic quantum difference operator as the ordered product of the algebraic monodromy operators over here, with the left product given by the line bound over here. So this will be so generically this will be an operator inside of the quantum toroidal algebra over here. And here this 0 to minus L is the path from 0 to minus L. And it's another type of solid. But for now, there's one thing maybe you can observe that this is the product of the points of the slope points over this path. And we know that the path, and actually we know that the points on the path is actually it has infinite number of the points. So what does it mean? It means that actually this is not the order product that we expected, because we usually require that this should be locally finite. But fortunately, if you use this operator acting on some equivariant K-theory of the quiver varieties, this product will be reduced to the finite product. So you can see that in this sense, this is well defined over the representation space. And the second thing is that, so this is the corresponding quantum difference equation. It's just the difference equation that we defined over here. Yeah. And the second thing is that it is independent of the choice of the path from 0 to minus L. And moreover, you can see the corresponding difference operator will commute with each other if you choose different line bundles over here. And so you can see that this is still an integrable system, a quantum integrable system over the Picard torus. So this is the basic of the construction. And the second thing is the application of this quantum difference equation. So how to do the computation and make it useful? The thing is that we're going to use this quantum difference equation to compute the monodromy for the de Broglie connections. So a surprising fact for the quantum difference equation is that it can be used to compute the monodromy for the de Broglie connection for the equivalent cohomology, for the quantum equivalent cohomology of the quiver varieties. So the de Broglie connection is a difference operator over this cohomology, such that the first term is the derivative with respect to this line bundle, and the second term is the quantum multiplication of the first chain class of the toroidal line bundle L. And it turns out that in the case of the fine type A, we have an explicit formula for this C1L. So you can see that the formula can be written in the following way. So the first term is the classical product, and the second term is a product given by, it's a term that has something to do with the trigonometric Casimir connection. So this E alpha and this E minus alpha, they are the root vectors inside of the affine GLN Lie algebra. So the formula for this kind of story it was proved by Maulik and Okounkov, but at first time we don't know whether these generators are all as the generators of the affine GLM, and the generators and the fact that these generators are something with respect to the affine GLM was proved by both Davidson and Schiffman first of all. So this is the key thing in our construction. And in our application, we'll omit the constant term. You can see that there's a constant term over here, but we'll omit this, like the case for the geometric quantum difference equation. So we'll omit the constant term and only consider the quantum multiplication as the following. And actually, you can just think about the constant term as some term from the gauge transformation of the equation. So anyway, the thing is that this differential equation, you can see it has only the regular singularities over here. So it makes sense for us to talk about what is the monodromy representation for this differential operators. And later we'll see that we'll consider the differential equation in terms of the degeneration limit of both geometric and algebraic quantum difference equations. So here we list two difference equations. The first difference equation is the difference equation from the geometric side, and the second difference equation is the geometric equation from the algebraic side. So maybe I should record here that both of the equations, for the first equation, it comes from the Maulik-Okounkov quantum algebra, and the second equation, it comes from the quantum toroidal algebra. So what does it mean for the degeneration limit? It means that we take the corresponding variables like p, q, and t to be the exponential of a kappa times something, and then we take the kappa goes to 0. In this case, actually, it's a really good exercise. You can see that the difference equation in this case would degenerate to the differential equation. So this is a really standard. This is a really standard degeneration. But the miracle is that if you do this kind of procedure to both of the quantum difference equations, you can see that both of the difference equations will have the same degeneration limit as the quantum multiplication of the first string class of the line bundle. So this is a really good result in the sense that if you want to compute the monodromy of this differential equation, we can first compute the connection matrix for the difference equation and do some degeneration limit to give some formula for the monodromy representation of the differential equation. So this is the basic motivation of having this degeneration limit. And so here's the main theorem, the first main theorem actually. And the main theorem is that if we want to consider the monodromy representation of this Gaborian connection, you can see that from the geometric quantum difference equation, it is generated by something that comes from the universal R matrix for the walls of algebra, or the geometric walls of algebra. And if you compute it by the algebraic quantum difference equation, you can see that it is generated by something that comes from the universal R matrix of the slopes of algebra. But for now, actually, we haven't achieved the final goal here, because this is the walls of algebra. This is the slopes of algebra.
Question. Yeah, I'm just confused. When you describe the reduction to the homology from this way, like, is it easier for you to do computations in K-theory for some sense?
Yeah, actually it is, if you want to compute the monodromy.
Why is that?
Because there's one thing that I have to say here, because you can see that the monodromy that I computed here is a fundamental group over the region. Mm-hmm. So what does it mean? It means that on the side of the quantum difference equation, it means that you take the fundamental solution from 0 point and take the fundamental solution at the infinity point. Right. So you can use the
like a monodromy goes from
the monodromy goes from here to here, and the computation and the details of computation is that you can take some limit of this quantum difference equation of this quantum difference operator in the infinite product, and you can compute that it is actually what you find after doing degeneration limits.
So why can't you do this in mode? You don't have just edited version of that, right?
And the thing is, the thing here is that you can just replace this automorphism by the K-theory, and this is the automorphism of the localized equivalent K-theory, and the localized equivalent cohomology. So in this case, this is isolated fixed one.
Right.
Yeah. So you can do this kind of computation. Oh, sorry. Oh, yes. There's one thing that I forgot to mention. Yeah. I replace all of the parameters by this PQT as this kind of
You work in first order in kappa,
Yeah.
Like what I don't understand, like in which sense K-theory is there?
It's just easier if you do the computation over the monodromy, over this space.
You can never have like
Yeah. And yeah, maybe I can say maybe I can use this sentence to say that actually in the case of the difference equation, it's much easier for us to see the behavior of the monodromy from something that might be complicated but might be easier to see it in some kind of a limit.
Again, the generation from this one.
Yeah.
Yeah, this maybe like it would be like more regular and something. Okay, maybe I can do that.
Yeah.
It's equivalent.
Sorry?
It's kind of equivalent to get out some fundamental things. It's algebra.
Maybe it's complex. Maybe it can be something. Yeah. So another application is that we're going to prove the isomorphism of the Maulik-Okounkov quantum algebra and quantum toroidal algebras over here. So the main theorem is that there's a rational form of algebra isomorphism between these two, but this is not true isomorphism. This is an isomorphism up to some constant elements. So I'm going to explain why this is the isomorphism up to some constant elements over here. So the strategy of the proof is that the first thing is that for the slopes of algebra, usually we can do the further decomposition in terms of the root quantum subgroup of the slopes of algebra by the holistic plus stoic factorization of the universal R matrix. And this can be done because this actually can be done because we have one of the insights is that for the case of the slopes of algebra of the function A, it can be isomorphic to the product of the quantum function K. So you can do this kind of a further factorization. But this is actually generally true, but only for the case of the function A, this can be really explicit. And moreover, using this factorization, each of the R matrix over here can define a root quantum subgroup over here. So we need another really refined embedding. So if we restrict actually there's a half algebra embedding from the slope of algebra to the Maulik-Okounkov quantum algebra with respect to the coproduct delta M over here and delta M over here. And the first delta M is just the delta M from the universal R matrix, and second delta M comes from the adjoint of the state element. So, but moreover, this kind of the half algebra embedding, it can be restricted to the half algebra embedding if we restrict to the walls of algebra on both sides. So this is really precise. And using this kind of the refinement, actually we can refine the results in the last section that the monodromy operator, the monodromy representations on the algebraic side, it can be generated by the something that is from the universal R matrix of the root walls of algebra. So in this case, you can see. So in this case, if you combine the result of the half algebra over there, actually the first thing is that this kind of the generators will give you that these two monodromies are actually equal to each other. But this comes from the computation for the degeneration. But moreover, I can see that these two generators are actually the same. And now combining the equality for the monodromy generators and the half algebra embedding over here, we could obtain that the universal R matrix for this walls of algebra and this geometric walls of algebra are actually the same. So what does it mean? It means that actually the walls of algebra and the geometric walls of algebra are actually isomorphic as a half algebra. And now since both the quantum toroidal algebra and the Maulik-Okounkov algebra are generated by the walls of algebra in the tautological classes, we obtain the main theorem. And so the certainty for the Cartesian elements comes from here because actually the generators from the tautological classes from the quantum toroidal algebra is actually a little bit smaller. And another thing is that from the side of the Maulik-Okounkov quantum algebra, there might be some other tautological classes that might not appear in the definition of the quantum toroidal algebra. Yeah. So So now I have finished the main part of the talk. So there are two diagrams I'm going to talk about. So the first diagram is the Q-theoretic equation for the quantum toroidal algebras. So a direct consequence of the result is that we can solve the Q-theoretic equation for the quantum toroidal algebra using the geometric construction of such module. Because general principle is that the tapping operator, as I defined before, is the solution for the geometric Q-theoretic equation. And for now, the above isomorphism implies that one can also use the capping operator to give the solution to the algebraic Q-theoretic equation for the quantum toroidal algebras over the module. And you can use the localization techniques, virtual localization techniques, and the non-abelian stable envelope techniques to compute the matrix coefficients of these operators over here. So it has a general formula looking like this. And especially in the case of the function A, the formula for the non-abelian stable envelope here and the elliptic stable envelope over here, and this Q gamma functions can be written explicitly using the equivariant localization formula. So you can see that for the case of the function A, this formula can be written explicitly in terms of the fixed form. And then digression 2 is that actually we have found that the isomorphism that we have shown before is the isomorphism of the rational form. But for the isomorphism of the integral form, this is actually much more different. But it turns out that actually you can do such a proof. And this is a proof in preparation that we can have an isomorphism of the integral form of the Hopf algebra on both sides. And the integral model for the quantum toroidal algebra is given by the semi-important K-theoretic algebra. And this is also another geometric story. But for the integral form of the Maulik-Okounkov quantum algebra is actually given by the algebra generated by the integral walls of algebra and the topological classes. So it seems to be obvious in the function play, but actually it's much harder to do this proof. And in this case, actually nothing about the quantum difference equation will involve in the proof. So in the end, I'm going to talk about some future directions for this kind of work. So actually, we can extend the techniques and theorem to arbitrary quiver type ML quantum affine algebras. And this is also a work in preparation. And actually, for the other type, it's much more difficult because the first thing is that we don't have the isolated fixed one basis. So we need to operate some other techniques to make sure it works. And the second thing is the special interest in the function A is that it contains lots of information for the theory of the symmetric polynomials and the integrable hierarchies. Because when we talk about something, for example, in the case of n equals 1, the corresponding localized equivariant K-theory is actually of the quiver varieties is actually isomorphic to the space of the symmetric polynomials in this case. And also one can use the isomorphism to give many geometric construction for lots of interesting objects in the integral hierarchies, which might shed new light to the integral hierarchies from the side of the quasimap counting. And this is actually some quasimap analogs of the story for the Gromov-Witten theory and the integral hierarchies. But this is a little different because in this case, most of the quasimap counting is accounting for the non-compact object. But in the Gromov-Witten theory, it's usually for the counting for the compact object. So this is a little bit different. Yeah. I think that's what I want to say today. Yeah. So thank you very much.
Thank you for that. So we have very few time actually before the next talk. So sorry, let's discuss probably some questions privately. Yeah, so we will start in 4 minutes.